Hello guys, welcome back to my YouTube channel again. And I think you all are really doing very well. And this is my last video about the energy balance. Previously, I had solved near about three problems, and I think till now you understood how to construct the energy balance equations according to the problem. And today, I have a very interesting question, real life basis. So just don't get nervous. The question is very large, pretty large. So again, I want to mention that I don't want to read out the question. Just pause the video and check it carefully. What they mentioned here, what are the assumptions they provided you, what are the data they provided you, and what they asked. Just pause, and if you want to try to solve it with your own, you can do that, and then step by step we will clear it. So I think you all have read out the question. So before we start, I have a quick request. Just don't just watch this video. You have to work with me, and then you can clarify what are the thermodynamics procedures we are making here. Okay. So now I am going to start the solution of the first part. They ask that create an energy balance for the circuit and calculate the total amount of heat energy transferred to the storage tank by the solar system on this day. So I have a question here before solving the first part. So what is the system we have to consider here? The collector, the solar collector, or the tank, or something else? I hope you all guessed it correct. Here the system is the entire solar loop, the solar collector, the pump, and the working fluid. So I just want to mark it. I am marking it with my green color. So for my first part, the system is solar circuit, solar collector, the pump, and the working fluid. So this is my system here for the first part. Now here is the crucial part I want to ask you before constructing the energy balance. How can the energy cross this system boundary? Here this is my system, so how the energy can cross the system boundary? There are three ways. One, the solar radiation enters here and it enters as the heat. Then second one is the electrical power entrance through the pump as the work. And third one is the thermal energy leaves into the tank. So before I want to start the calculations, I just want to make the energy balance equation here. We know the system will be summation of delta work, summation of delta heat, and summation of delta E material. So here there is no material transfer, so it would be 0. But here is the heat and work transfer. So we have to conclude that. And for the next part, we have the system that would be kinetic plus potential plus internal energy. So here there is no storage. So there will be no heat, like no energy storage. So and it's a steady state problem. So it all would be 0. So only now we have the system that is equivalent to summation of the work transportation and summation of heat transportation. And here we have the work transportation is only via pump work. So we can write out pump work, and that is the mechanical work. And here, if you construct the energy balance equation, then solar radiation is of the heat, then solar radiation enters as heat, and the heat leaves into the tank. So basically, it is going inside through the solar system, then it's absorbed by the tank, or it leaving the system, and it's going to the tank. So now, if you want to construct the equation, then it will be here it is 0. Now I am constructing this equation using these two, so it will be working pump mechanical plus Q solar minus Q tank, it would be 0. So we can easily calculate the collected heat value or the solar heat value, because they have provided you the equation here, and they also mentioned the data, how many collectors, what is the efficiency, and all those. So here I can write it down. W pump mechanical will be, we know work power means work upon time, so work will be powered into time. So they mentioned here the pump power. The pump power is here. You can check that 80 watt. So I have to convert it in kilowatt. So it would be 0.08 kilowatt, and the time is for, they mentioned as 6 hours. So now if you calculate it, you will be get 0.48 kilowatt hour. Now if you want to calculate the Q solar, then it would be, or Q collector, they both are same. Then it's the formula here they mentioned in collector, in efficiency of collector, it's eta into the area and the irradiance I dash day. Then the value will be, here the main confusing part here is there are two collectors of two, like two pieces of collectors, so you have to calculate the area of the two pieces. So it would be 2 into 2, then it's 4 meters square. One collector have the area of 2 meters square, then the two collector have the area of 4 meters square. Now put in the formula, the eta collector they have provided 0.45, and area they mentioned 2 meter, and for 2 it's 4 meters square, and I dash day they have provided it 1.7 kilowatt hour per meter square. So if you calculate all these things, then it will be 3.52 kilowatt hour. So now if I going back in this equation, then Qt will be Wp mechanical plus Q solar. So 3.52 plus 0.48 and the ultimate answer will be 3.96 kilowatt hour. I think you have understood all these things and you don't have any doubt. So here the system where the collector and the pump and the working fluid. Now let's get solve the second part. So they asked here is the final temperature if no water is drawn off. So here what would be the system for us? Here the system will be storage tank and the water. So I am going to mark it with orange color. So this is my system. This is my system here in the second question. So it's the storage tank and the water. And here we only have to deal with, like, if you construct the energy balance equation, then we all know the system will be same, like summation of del Q, summation of del W, and summation of the material transfer. And again, we have the system, the kinetic, the potential, and the internal energy. So here there is the system is steady, and then we have to remove the kinetic and the potential, only the internal energy will be remaining. And here also there is no work transfer and no material transfer, only the heat energy will be there. So we can write it down that du will be summation of del Q, or we can write it down, it will be as the Q of the tank. So now we all know the heat equation is mCp delta T, and here the temperature are the difference of T2 minus T1, and here the m will be the mass of the water and the specific heat capacity of the water at constant pressure. Now put the data they are mentioned here. So T2 is mentioned, T2 we have to find out, and T1 is mentioned, and mass of the water and the specific heat and density is mentioned. So we can write it down. We all know mass is not mentioned here directly. We all know that density is equivalent to the mass upon volume. So mass will be density of the water and volume of the water. And they mentioned the mass density and the volume of the water here. So we can easily calculate it. So we already figured it out, the Qt in our previous problem. The Qt is 3.96 kilowatt. So for easy solution, we have to make it in kilowatt second. So it would be 3.96 into 3600, and we have the mass of the water they mentioned as 990, and Cp is mentioned as oh yeah. So volume will be, I am putting the mass of water here as the rho cross V. So 990 cross 0.2, and Cp is 4.18, and you have to figure it out. T2 and T1 is mentioned at 10 degree. So you might have the question, why write it down the volume as the 0.2 So here we have 200 liter of the volume. So if you convert it in liter to meter cube, then it would be divided by the 1000. Now if you calculate all of those things, T2 minus 10, it will be equal to 17.2, and then you have the final temperature of the tank as 27.2 degrees Celsius. I think you understood it. So that is our second part they asked. Now we have to move the very crucial part here. They asked after the sunset the electric heater is turned on. How many hours must the heater be on to heat the upper half of the buffer tank? So here they clearly provided the structure, the upper half of the tank and the lower half of the tank. So the main thing is that we have to take the half of the tank only. Why so? Because the tank is stratified and the problems states there is no mixing of those things. So the total mass here they mentioned as, yeah, we have, I think I missed some data, 0.6. Okay, so here if you calculate the mass of the water, it would be 990 cross 0.2, and it would be 198, and it is the total mass. And now we have to take the half of the mass, then it will be upper half will be of the mass of the hot water will be 198 upon 2, and that will be 99 kg. Yeah, and here if you have to calculate the time, like when the heater, how many hours must be the heater be on to heat the upper half of the buffer tank at T3 6 degrees Celsius. So now you have to calculate the heat, like when the heater is on, how much heat is absorbed. Then heat will be Q and the mass of the hot water and the specific heat capacity and the temperature difference. So previously the temperature was 27.2. Now we are going to T3 as 60 degrees Celsius as mentioned in the problem. So now the mass of the hot water is 99 kg and the Cp is 4.18 again, and T3 is 60 and T2 is 27.2. And if you calculate it, then you will get 13,600 kilojoule. And if you want to make it in kilowatt hour, and why we are making so? Because they have provided the efficiency and the power, so we have to calculate, like when we are required the time, so we only have the formula regarding the power and the work. So we all know power is the rate of the work. So here we have to calculate, and here the work is in the mode of the work is the energy, and we can substitute it by the heat. So here the heat energy we got 13,600 kilojoule. Now we are making it in kilowatt hour, then it would be 13,600 into sorry, it would be divided by 3600, then it would be kilowatt hour. and you will get 3.78 kilowatt hour. Now we have the efficiency of the electrical pump motor. Sorry, the efficiency of the heater. We are considering is on the heater here because it is our system in this problem, and it's 0.95. So I can write it down. P effective will be eta electrical into power of electrical. So effective power would be 0.95. They mentioned here as 95%. Oh, and the power of the electric motor is 3.5. So 3.6. So it will be equivalent to 3.42 kilowatt. So now if you look that, we all know power is also Q upon time. I mentioned here, or work upon time. Actually, it's power is the meaning of the power is how the energy rate. So here is the energies as the heat energy, and here the power effective power would be also equivalent to this one. And we have the heat energy here. We calculated. Now we have to calculate the time. So just substitute the value of the Q. We calculated 3.78 here, and the effective power we have calculated here. To substitute it, then you can find out the time easily. So now the time will be Q upon P effective, and the Q is here 3.78, and P effective we calculated as 3.42. Write down the unit. So kilowatt will be cancelled, and when you calculate the time, it would be 1.1 hour. That is our part C. We have calculated. Now we have the question, the last one. The temperature in the upper half of the cylinder has reached T3 now, and how much water can be made available for use if the outlet is mixed with the fresh water beforehand, resulting in an outlet temperature of this. So, and without additional heating we are doing. So now the main problem is that, like, we are now opening this mixing valve here, and this water is now mixed up. So now we have to think that is this still is an energy balance problem? Yeah, it still is an energy balance problem, and now we have to deal with the valve. So here we have to solve. So the valve will now control the cooling water, the fresh cool water, and the fresh and the hot water. So we have the hot water here, mass of the hot water, and temperature difference is now T3 minus T4, and the cool water is mass of the cool water, and T4 is mentioned as 37. So T4 minus T1. So we all know the mass of hot water is 99. The previous we have solved here in this part. So, and we have T3 as 60 and T4 as 37. So we have to calculate the mass of the cooling water, and T4 we have as 37 degree. and T1 is 10. So if you calculate, then you can get the mass of the cool water is as 84.3 kg. Now the total water balancing by this valve will be mass of the hot water and the mass of the cool water, and if you add those, you will get 183.3 kg. Now they have asked you how much water in liters can be made available. So they have asked in the liter. We have to find out the volume. So actually the valve is handling this much of water totally, the liquid. Then the total volume will be V4. We all know mass density means mass upon volume. Then volume will be mass upon density. And we have total mass here 183.3 kg. And they mentioned the density as 990 kg per meter cube. So if you balancing those, now it would be 83.3 upon 990 1 upon meter cube, and if you want to convert it in liter because they have asked you, then you have to multiply meter cube to liter, it would be multiplied with 1000. Then you will get 185.15 liter. That is our final answer. I hope you understood all of those parts. Thank you. Bye bye. See you in next video.